So hello, we're starting our first session, and this is my great pleasure and privilege to introduce Marc Paterno, who is a computer scientist at Fermi National Lab, and HCF Group was working with Marc more than probably for about 15 years. I remember when Marc and Chris, right, Chris came to our office in Champaign and described the problems with their high energy specific data, and I thought myself, oh my gosh, we have a problem. And there was a problem, so they had looking for me. And since then there was no problem, and I participated only for HC5, and that's what he will be doing about big data in high energy physics and computer changes in the secret of the universe. Thank you, Marc.
So I'm actually with this slightly grandiose title here. So I work at Fermilab, which is America's particle physics and accelerator laboratory. So I'm going to be telling some stories about what scientists at Fermilab do, at least some of the high points that have been that have come around during the course of my career there. Along the way, I'm going to be talking about the data-related challenges that we've experienced in fundamental particle physics research. Very little of this, so the experiments I'm going to be talking about have not traditionally been users of HDF5, but I'll be ending with a data challenge that I suspect is going to require new technology to which we are not accustomed. So we'll start out with what is fundamental physics. So as physicists currently understand the world, it's composed of a few fundamental particles and a few forces through which they interact. So the diagram up here is part of a picture that we call the standard model. Right? The table shows what we currently believe to be the fundamental particles. On the left-hand side of the table are things that make up matter. So these are quarks and leptons. The quarks are the sort of things that make up the particles in the nucleus of an atom. And the leptons, one of them is the electron that orbits around the nucleus. So between them, quarks and leptons kind of make up matter. Right? The groups on the left have the horizontal rows on that chart shows families of particles that share some fundamental features, most importantly, some kinds of charge. One of these is electric charge, that's the one that everybody's familiar with, but there are other charges that exist in nature, and these are related to the fundamental forces. Right? The forces are gravity, which doesn't show up in the standard model, and the electromagnetic force, and then there's also the weak and the strong nuclear forces, right? And all of these are studied at Fermilab. The particles on the right side are the things that are related to the different forces. The most familiar of these is the photon, the gamma up there. That's the particle that's associated with radio waves, visible light, X-rays, all that kind of thing. It's what's called the force carrier for the electromagnetic force. The photon is massless. The W and Z particles up there are force carriers for the weak force. They're very massive, right, compared to almost everything else on this table. Right? And the gluons, the G up there, is the force carrier of the strong force, the way quarks interact and what holds them together inside of a proton, for example. And that's another massless particle. And in the center, almost invisible in the gray there, is the Higgs particle. And that's related to why all the other particles, or at least some of the other particles, have a mass. Right? And the Higgs particle is itself a very massive particle. So particle physicists at Fermilab conduct experiments, both at Fermilab and elsewhere, to better understand the interactions of all these particles and forces. They also look for new particles and sometimes even discover them, and that's some of the discoveries that I will be talking about. Missing from the standard model is gravity. Gravity is much weaker at small scales, but it's absolutely dominant at large scales. Like the solar system, gravity is what holds together galaxies, and gravity is, to a large extent, what determines the evolution of the universe. So physicists at Fermilab, in addition to studying the smaller scales of these particles, also studies the larger scales and how does gravity influence the universe at large and the structures we see in it. So I'm going to be talking about some of the exciting discoveries in this picture. So I'm going to start actually before my time at the lab. So before I got there, this is what a experimental detector looked like. Right? In the 70s and 80s, much of particle physics was done with what was called bubble chambers. So this is a picture of a 15-foot bubble chamber. I think it's the biggest in the world at Fermilab. They're no longer used. This one is sitting outside of a detector building facility now as a piece of artwork. But as recently as the 1980s, this was still kind of state of the art. Right? In a chamber like this, charged particles created by crashing high-energy particles into various targets would leave trails of microscopic bubbles, right? Thus named bubble chamber. We call these trails tracks, and the distribution of the bubbles, right, the density and the exact curvature of the lines they made would be used to identify the types of particles that left the trails and the energies of the particles. This is what data analysis looked like in the days of bubble chambers. Okay? The woman in the picture is studying an image taken by that bubble chamber. On a personal note, it was a bubble chamber image like that actually caught my interest in particle physics. When I was like 10 years old, at the local town library, there was a physics book with a cover like that on it, and it just looked cool. That got me interested in physics. So to analyze an image like this, the human ability to recognize patterns was absolutely required, as well as careful measurements of the tracks on the things. Electronic computers couldn't handle this. This is the entirety of the team who originally did all the scanning at Fermilab. Computers this time were people who did the calculations of the curvature of tracks. Right, and did a statistical analysis. An experiment would take maybe 6,000 or 10,000 pictures a day at most, and the data handling problems were pretty small. So in 1977, the bottom quark, so the B on that list of quarks, and the first poster that I showed, was found at Fermilab. And so a partner, the top quark, was then expected. And for nearly 20 years, bigger and bigger experiments, bigger accelerators were built trying to find it. So now I'm going to fast forward to my time at Fermilab. This is what Fermilab looked like when I first arrived. So the big circle ring there is actually the surface visible footprint of a 4-mile circumference accelerator. So in 1987, the Tevatron accelerator at Fermilab started up. It was the first superconducting accelerator in the world. It had almost 1,000 superconducting magnets around a 4-mile circumference. They would collide beams of protons and antiprotons. Yes, Fermilab made antimatter at high energies to try to create and observe new particles, like the top quark. Fermilab, so the Tevatron was host to 2 big detectors called CDF, the one on the left, that's Collider Detector Facility, and the one on the right was D0, boring named. It's named after the location in the ring where the detector was built. Because it was my thesis experiment, I'll talk mostly about D0. So in, I think this was 1990, yep, 1990, Time magazine had a cover article on big colliders, and it discussed, among other things, the Tevatron. So this is the picture from there. That's me in the lower left-hand corner. So this is my claim to fame. I was in Time magazine once. Yeah, you can't identify me unless you know it was me. I was part of what was called the central calorimeter at D0. And that was one of 7 major subsystems in the detector. Oops, not yet. All right. So when D0 first saw data in 1992, right, and these experiments continue for many years or decades, so, and getting upgraded multiple times. So when you look up statistics for an experiment, it's very difficult to nail down even some general numbers because experiments are continually being upgraded. But when this detector was first built, it had about 115,000 separate readout channels that had to be put together to form the equivalent of one of those bubble chamber images. Right? So the size of the data for one event was about 500 kilobytes. Beam crossings in the accelerator, and so possibly interesting collisions and containing possibly interesting particles and interactions to study, would happen every 3.5 microseconds. So about 300,000 times a second, this half kilobyte of data would get read out and had to be analyzed for patterns indicating that something interesting had happened. So we went from 6,000 pictures in a day to 300,000 in a second to look at. Obviously, that had to be automated. So a multi-tiered system of computers was used to analyze the data in real time. The first layer of the first tier of that computing would take in the data, 500 kilobytes every 3.5 microseconds. The last tier reduced that to what we could actually record, to write out 2 events per second. And so that software was required to look at the many input to decide which are the 2 most interesting to save. You can't just pick them at random or you'd never see anything interesting. So it's a very intense computing challenge rather. Back in the day, this was done on a farm of 50 VAX 4000 microcomputers, each with a massive 83 megahertz chip in it. And that was the state of the art at the time. The output of that was about 2 events per second, so about a megabyte per second. That adds up to about 25 gigabytes of data in a 24-hour running period. And an experiment like this would run as long as the accelerator beam was on. We'd take shifts all night to collect data. Offline, away from the detector, no longer in real time, all this data had to be analyzed. And so we call that process reconstruction. So reconstruction was the automated equivalent of the people's pattern recognition, recognizing that, oh, look, it looks like a particle went here with thus and such energy. And then to identify what happened in the detector. So D0 and CDF at this time used 8mm tapes to store valuable data. It was a new technology at the time. 1991 was the first time that a particle physics experiment used tape like that. And each tape could store a whopping 2.5 gigabytes of data. Right? So D0 would write out 10 tapes a day from the control room of the experiment. In 1993, the accelerator was shut down for a couple of months for some upgrades, marking the end of what we called Run 1A. At that time, the CDF experiment had seen a hint of the top quark, but not enough of a hint to be able to claim a discovery. D0, he really hadn't, was a much newer experiment, really hadn't seen it yet. But when the accelerator was restarted, the beam intensity was much increased. And then the race was really on to try to find the top quark. And, okay, I think I just let somebody else into the meeting. Hopefully that's okay. So this is the Fermilab auditorium in 1995. If you have a keen eye, you can see me and my wife near the top of the picture at in the auditorium here. So in 1995, the top quark was finally discovered. CDF and D0 simultaneously published papers. This is the photograph of the auditorium when the public announcement was first made. This made big headlines. Particle physics generally doesn't make big headlines, but this was all over the world newspaper headlines. So what went into that discovery? For each experiment, for each of the experiments, the top discovery was based on observing less than a few dozen events that looked like top quarks. Right? In just run one, D0 wrote to tape about 20 million events. And remember, we only wrote out 2 out of about every 300,000 that came into the detector. D0, I happen to know the exact number, it was 17 top candidates that we saw in that publication paper. The reconstruction output for that 20 million events was 7 terabytes of data. So it was 3,000 of those 8mm tapes. The Run 1B data set, part of which was used in this analysis, was 70 million events and 15,000 tapes, more than 40 terabytes of raw data, all to give 17 top candidates. So to get there, the automated reconstruction needs to be sufficiently well understood so that the experiments could predict how many top quarks do you expect to see given its mass in a data set like this. Right? On the machines of that day, the reconstruction of one event would take about 30 seconds. So this was a lot of computing power that went into this. Well, a lot of computing power, except for Run 1A, D0 had a farm of 24 computers doing that work. That was all that the experiment could afford. CDF had a similar scale. And in addition to analyzing the data, simulations are necessary so that you can understand your analysis well enough to make the predictions. And in fact, more effort went into doing simulations than into the data analysis. These data sizes and resources, they don't sound like much today, when we look at what's available today. But at the time, we were pushing the limits of what was possible with the available technology. And this is basically a recurring theme in fundamental physics, right? We're always pushing the technology. Every once in a while, people ask me, well, when will a computer be fast enough? Or when will the I/O be fast enough? Or anything like that. And the answer is basically never. If you give me a machine that's 10 times faster, I will come up with a problem that's 20 times harder, and you'll still need a faster machine. And this is what what fundamental physics does. So now I'm going to go from the smallest scale that Fermilab studies to the largest scale, to cosmology and the large scale structure of the universe, and also 10 years further on. So now we're in the 2000s. This is a picture of a little piece of the sky. Most of the dots on there are not stars. They're actually galaxies. Right? So the universe today contains a vast number of galaxies, each containing a vast number of stars, and they're not spread out. The galaxies are not spread out evenly through the universe. They're formed into large structures, galaxy clusters, superclusters, and voids that have almost nothing in them. We don't fully understand why this is the case, but we have a good story, a theory, about the development of the early universe, and the theory makes predictions about what we should see. And we can test those predictions. That's what makes it a theory. So immediately after the universe began, it was too hot for protons and electrons and even photons to exist directly. But the young universe was expanding very rapidly. And as it expanded, it cooled. Within about a second, it had expanded and cooled enough for particles, protons and neutrons, together called baryons, to exist. And at that time, the universe was so dense that it was opaque to light, right? A photon that started traveling would immediately get absorbed, and so the universe was opaque. Sure hope this works. Okay, I'm attempting to show. There we go. Okay, so the early universe wasn't a uniform superbaryons. There were little variations in density, right? And so it was more like a stew. Starting in places where the density was high, almost instantly there was a burst of vibrations. So this is showing these vibrations in the stew. These are pressure waves, like sound waves. So this comes by a name we call baryon acoustic oscillation. They traveled outwards as the universe expanded and cooled. After about 400,000 years, the universe had cooled enough for light to be able to travel through it. And at that time, the universe became transparent and the sound waves froze. In the areas where there was a high density, more galaxies formed. And in areas with low densities, fewer galaxies formed. Or so the theory predicts. So if you could measure the locations of the galaxies carefully enough, you could then calculate the distance between the galaxies. And there's a lot of pairs out there. You do this for every pair and plot the result. And this eventually shows a little bit of a distribution. You do this if you have a big enough data set, measure it carefully enough, right? It's possible to see a peak in this distribution if this theory is right. You get a distribution that looks like this, and there's the baryon acoustic oscillation, the BAO peak. So the theory says that we should see this and where it would appear. So we looked for it. Whoops. So this is the telescope used by the Sloan Digital Sky Survey. Right? It was the first survey of its kind, taking digital pictures of the sky. We'll get in a moment to what picture means in this case, because it's a little bit weird. But it recorded locations and distances and shapes and many other features of tens of thousands of galaxies. And from these data, we're able to measure the distance between the observed galaxies. This is a plot of a late version of the SDSS data. Right? This isn't a photograph. This is this is what in particle physics and astronomy often goes by the name of visualization. We don't do exciting animations most of the time. This plot shows about 0.5% of the sky. It covers an area that's 6 billion light. Pardon me. About 6 billion light years wide, about 4.5 billion light years high, and about 500 million light years thick. Each dot up there is a galaxy. The color shows the distance to the galaxy. So yellow is closer, violet is further away. And this image has in it a few 100,000 galaxies. In 2005, Sloan had less data than this, but they had data from about 40,000 galaxies. And with that, they were able to verify this BAO oscillation peak and measure the characteristic distance and thus confirm or at least lend more confirmation to the theory that predicted this. Right? This was the largest astronomical data set collected up to that time. The SDSS camera, I think it was the biggest camera in its day. It was 138 million pixels, and a single readout was a little bit more than 2 gigabytes. When I said images are a little bit weird, in its survey mode, the camera didn't actually take snapshot images. Instead, what they would do is open up the shutter of the camera for almost a minute, and the telescope would move with the sky in such a fashion that one of these galaxies, a distant point, would travel down the row of light-sensitive elements on the camera, thus allowing it to get more integrated light shined onto the camera, allowing us to see fainter and therefore more distant galaxies. By 2006, SDSS had about 25 terabytes of raw data. Right? That includes images taken with this camera and also spectroscopic measurements that were very complicated to make of tens of millions of galaxies. The one suitable for this BAO measurement was a few tens of thousands. Every one of those images had to be processed and the galaxies identified and picked out from things like asteroids and comets, and even things like man-made satellites or airplanes flying by overhead. Let's see, I cannot admit whoever that is. Right? So the galaxy catalog used for this was about 1 terabyte. And unlike most of what went into high-energy physics, it was actually a database, not special purpose files. SDSS is still containing data long after this discovery, although Fermilab's no longer associated with it. Its most recent data release was 245 terabytes, and that's new data in that release, adding to about 400 terabytes that they had already released. And so the astronomy programs like this make their data available to the world. So if you want, you could go to the Sloan website and download any piece of their data or all of their data if you want it. And newer sky surveys will create even larger data sets. And there's an experiment that is soon to be seeing first light that will have data sets that dwarf what the Sloan took. So next I'm going to move up to the 2010s and back to elementary particles. So this is what Fermilab looked like in the early 2010s. The Tevatron ring is the one that up at the top. What looks like a bigger ring, it is actually smaller, it only looks bigger because it's closer, was a new detector, not a new accelerator rather, built to increase the intensity of the beams. Right, and now trying to measure the top quark and looking for the Higgs particle. Computing moved from being separate facilities run by each experiment to a computing grid shared by both experiments. The data were now too big and coming too fast to be able to be written to tapes by in the individual experiment halls. So the data were now shipped by a local network to a central facility. So our computing needs had exceeded what a single experiment could support. We had to marshal the whole resources of the laboratory to support the experiments. At this time, the experiments were recording about 100 terabytes of data per year. So back to our particles poster. At the end of the Tevatron era, CDF and D0 had both observed some hints that there might be a particle with properties like those predicted for the Higgs particle at the middle of this picture, and with a mass between 120 and 135 times that of the proton. And they published jointly a paper announcing this in 2012. Well, 17 years earlier, CDF and D0 had each been able to discover the top quark. And the top quark is as massive as 175 protons. The single quark is almost as massive as a gold atom. Right? So why in the world was the Higgs, which is massive but not as big as the top quark, why wasn't that seen? The problem is that the interactions the Higgs undergoes is much weaker than those of the top quark. So they were much rarer to produce. So what was needed for a clear discovery was a lot more data. So 100 terabytes a year wasn't enough. This is a picture of CERN, the big particle physics laboratory in Europe, and the Large Hadron Collider, the LHC. Right? It's currently the largest and most powerful particle collider in the world. It's got a circumference of about 17 miles, so it's about 4 times longer than the Tevatron, and it has an energy that's 7 times higher than the Tevatron. And so it can make particles like the Higgs a lot more readily than the Tevatron could. It also has more intense beams and collides them more frequently. So the data rates into the detectors at the LHC is a lot higher than they were at the Tevatron. And the accelerator and the detectors themselves were a lot bigger, so their data sizes are a lot bigger than the experiments at the Tevatron. This is a picture of the CMS detector, one of the 2 general purpose detectors at the LHC. Right? The name CMS, you can see there's a person near the bottom of that. So amusingly, CMS stands for compact muon solenoid. Compact in this case means 21 meters long and 15 meters in radius. That actually is the smaller detector of the 2 general purpose detectors at the LHC. Muon is the particle mentioned in that table because CMS is specifically designed to measure muons very accurately. And the solenoid is the type of magnet that is wrapped around this detector. It's so big that you don't even see it in this image, but it is the most powerful electromagnet in the world, at least at the time of its building. When it was first built, remember these detectors undergo upgrades, and CMS has already been upgraded. CMS had about 75 million readout channels. So a single data readout has 75 million channels to be looked at. During its first run, the LHC delivered a beam to the detectors every 25 nanoseconds. So 40 million times a second. That's actually a shorter time, a faster collision rate than it takes to read out the detector. So when analyzing data from one beam crossing, there would actually be some signal left in the detector still being read out from the previous crossing. So the business of pattern recognition, in addition to sorting out the data from the current collision, has to deal with leftover from the previous crossing. And because that's not bad enough, the beams were so intense that each crossing would have about 20 collisions in it. One of them hopefully being an interesting thing that you would care about. So with this level, with this rate of interactions happening, the multi-line online reconstruction system had to be even better than what was dealt with before to pick out the most interesting events to record, because while they were getting 40 million crossings a second, they could write out about 400 events per second. Well, about 1 out of every 5 billion collisions at the LHC produces a Higgs particle. In 2012, CMS and its sibling Atlas announced the discovery of the Higgs particle. Right? Here's world headlines. Only the second time in my lifetime that I remember, particle physics being on newspapers. So for this discovery, each experiment had amassed a pretty huge data set. And this time, instead of having the resources of one laboratory, the computing resources to do this were spread around the world. One laboratory couldn't support these experiments. Fermilab hosts one of 7 CMS, they call them Tier 1 computing sites, the only one in the US. Fermilab actually supplies 40% of the Tier 1 computing capacity for CMS. At the time of this discovery, Fermilab had 15 petabytes of storage on disk just for CMS data. And we also had an additional 22 petabytes of tape storage. Right? We had about 3,300 cores and about 300 server nodes to do processing of this data. 2 of those nodes matched the entire computing capacity available to CDF or D0 at the time of the top quark discovery. And as I said, it was worldwide computing. CMS didn't have only the 3,300 cores at Fermilab. They had access to about 64,000 cores around the world to do their computing. So in the Tevatron, the computing demands had gone beyond what experiment could provide to need the resources of the whole laboratory. At this time, the needs have gone beyond what one laboratory could supply, and global marshaling of resources was necessary. So worldwide computing grid. Later this decade, Fermilab is going to be facing a different and maybe bigger data challenge, one that touches upon both particle physics and cosmology. So here we are back to this poster. So neutrinos, the things at the very lower left part of this diagram, they are uncharged leptons, right? So the one lepton that we all know and love is the electron. It's charged. The muon and the tau, the other 2, they're kind of like the electron, except they're heavier. Well, neutrinos are uncharged, right? And they are the least well understood piece of the standard model, mostly because they're very hard to observe. So every second of your life, there's about a trillion neutrinos going through your body, most of them coming from the sun. In a long lifetime, maybe one will interact. So it's a big source of radiation, not terribly dangerous. Don't worry about it. Right? That's because they only interact through the weakest of the forces up there. One way to think of this is the following. If a hydrogen atom were the size of a football field, the proton, its nucleus, would be about the size of a pea sitting in the middle of the field. Right? And the electron would be a little dust speck orbiting around just outside the thing. Right? A neutrino coming through this atom would be another dust speck that basically has to brush up against that pea in the middle in order to interact. There's a lot of room to get through without bumping into the pea. That's why that is the kind of scale you're dealing with for neutrino interactions. Well, since the shutdown of the Tevatron, most of the experiments at Fermilab have been studying neutrinos. This is a drawing, not to scale, of the next big facility being built at Fermilab, well, and elsewhere. Right? So the biggest construction projects at Fermilab now are associated with an international neutrino experiment, the Deep Underground Neutrino Detector, DUNE. So DUNE is going to have a few detectors on site at Fermilab, and also some very huge detectors at the Sanford Underground Research Facility, SURF. That's in South Dakota and about a mile underground in a now out of business mine. So that's about 800 miles away. So Fermilab is going to generate an intense neutrino beam and shoot it through 800 miles of ground at the detector. But neutrinos interact so little that it kind of doesn't matter that there's 800 miles of rock between us and them. You know, not many of the neutrinos are going to be interacting anywhere. So DUNE is going to have several. It's still still being built, and what several means is somewhere between 2 and 4. Large detectors at Fermilab. So large in this case is an individual detector module being 66 meters long, almost 20 tall, almost 20 wide, filled with 17,000 tons of liquid argon at about 300 degrees below 0 Fahrenheit. So Fermilab is going to shoot the beam of neutrinos from Fermilab at these things as their target. So what we're looking for requires knowing a little bit more about neutrinos. So if you recall from that poster, there were 3 different types of neutrinos. We call them flavors, one associated with each of the 3 different leptons. So there's an electron, muon, and a tau neutrino. Well, perhaps the weirdest thing about neutrinos is that they change flavor while they travel. So imagine you started out with a truck full of chocolate ice cream bars at Fermilab, right? You pack them into the truck, drive them 800 miles to your friends at SURF, open up the truck, and now inside are vanilla and chocolate and strawberry ice cream bars. That's kind of what the neutrinos do. Right? So Fermilab is going to make a beam mostly of muon, almost purely of muon neutrinos, but will observe other things at the far site. How does this happen? Actually, we don't really understand it terribly well, but we do see that it happens. We've observed it in other experiments. So DUNE would be the first experiment to observe. We call these oscillations. It's designed to make more precise measurements of these oscillations of the properties of neutrinos to try to help us understand how this happens. Like the standard model can't explain how it does. It has kind of built in that it does. We would like to have a better theory, a better story that explains why. So Fermilab will shoot a few trillion neutrinos every second in very brief bursts. So a burst that lasts a few microseconds, I think. With about a second between bursts. For every one of these bursts, the Dune detectors will read out 6 gigabytes of data. So we'll be reading out 6 gigabytes of data about every second, all day, every day for years. Right? That's a moderately large data problem. All to see a prediction of about 1 interaction every 4 hours in one of these detectors, because neutrinos don't interact very much. Right? So that's 6 gigabytes of data a second. But Dune's also going to be looking for astrophysical events. So stars like the sun are held together by gravity. Right? Gravity doesn't crush a star to nothingness because the forces involved with burning the fuel of the star make it expand. So those forces push against gravity, and so a star stays in a nice, neat ball most of its life. If a star's massive enough, when it runs out of fuel to burn, it collapses because of the gravity. Right? This is a supernova. Right? When a supernova explodes, according to our current calculations, about 99% of that gravitational binding energy that was holding it together turns into a burst of neutrinos that lasts maybe 10 seconds. Right? That burst is so intense that the neutrino wind blows the stellar atmosphere away. Remember, trillion neutrinos going through your body every second, maybe one will interact. This is a neutrino burst so powerful that the impact of the neutrinos blows the atmosphere of the star away. Just hearing the phrase neutrino wind strikes me as utterly bizarre. Well, a core collapse supernova, that's what this is, at 20,000 parsecs, so like the far end of the galaxy, could result in 100, maybe a few hundred interactions in a Dune detector. Right? So a supernova anywhere in our galaxy should be visible in this detector. Such supernovas happen a few times a century. Right? However, the Dune detector is going to be looking for these things, and we're expecting an alarm that there may have been a supernova about once a month. Well, mostly false alarms, but they got to look at them anyway. Well, the time window necessary to read out the detector to observe the supernova is on the order of 100 seconds. So we get 6 gigabytes in 1 second, but that's actually a little bit of a cheat because the beam width, the time when the window is open to read out the detector for that 6 gigabytes is only about 6 microseconds. So the detector is actually reading out a gigabyte per microsecond. The supernova window that they need to collect data for is 100 seconds. So a single newt supernova readout for this detector or supernova candidate is going to be 100 terabytes. So that's the data challenge that we have coming up in the future, that this detector has to be capable whenever it gets an alert from a telescope that someone somewhere in the world thinks they've seen a supernova. They have to read this whole thing out for 100 seconds, collect 100 terabytes of data, ship it up from a mine a mile underground in surf, ship it 800 miles back to Fermilab, to the computers to deal with, to reconstruct it. So I'm hoping somewhere over the next couple of days, somebody will tell me how to do that. The future should be interesting. Thank you.
Thank you, Mark. Any questions?
Yes, Tom.
I worked with you for 5 years and I didn't know most of this, obviously, enlightening. Did I understand correctly that there isn't actually a tunnel 800 miles long from Fermilab to Stanford that you're just shooting neutrinos through the ground?
Yep. So we're doing this already, have been doing this for many years already. There's an experiment that I didn't talk about that you in fact work with, Tom. NOVA is embarrassing, don't remember the number, 400 or so kilometers, the NOVA far detector. And yeah, we shoot a neutrino beam through the Earth Yeah, some of the neutrinos will interact in the rock once in a while. You know, we need to make this crazy intense beam just so that there's enough neutrinos that something will appear, you know, will interact at the other detector. I remember a Star Trek Next Generation episode where Geordi LaForge built a neutrino searchlight to signal the Enterprise to come get them. It was perhaps the worst bit of physics I've ever seen on TV. Love the show, but boy, and worse than that, they had to, the special effects. Geordi was able to see the neutrinos reflected out of the atmosphere, right? Like a flashlight on in a misty day where you could see the beam. Wow, the intensity of that supernova flashlight, or that neutrino flashlight must have been like a supernova to be able to see that. I was impressed.
What's 800 kilometers away?
So the position and the location was chosen in kind of in concert with the energy of the beam to maximize the oscillation signal, right? So it really is an oscillation. So depending on where you measure it, you'd expect more or fewer of the muon neutrinos to appear as electron neutrinos. So it was landed there because that's a local maximum for the number of electrons that will appear. Yes.
That looks shape-wise like it's highly directional. But when you get a notification from around the world that there's been this supernova event, how focused do you think it will be on the direction with those neutrinos that you coming?
So the detector is, I should say, directional like this in order to be, to present as much sensitive material in the direction of the neutrino beam as is possible. But supernova can come from anywhere. It'd be most unlikely to be kind enough to line up. But the amount of neutrinos that are produced is so enormous that we would still expect, it's a difficult thing to calculate, but it's 100 or maybe a few hundred neutrinos in each detector, all coming from the same direction. And so it will be very easy to distinguish between that and anything coming from the beam. Also, the beam, the actual delivery of the beam is a handful of microseconds out of each second. So it would also be most unlikely that much activity in that supernova, detection would align in time. So it will be very easy to distinguish if it ever really happens. Hopefully we don't get an event with thousands and tens of thousands of neutrinos, because that would mean the supernova is very nearby and that could ruin your day.
But will you get direction from where it comes, or you're also looking at telescope data?
Well, so the telescope data would be much more accurate to say where it comes from, but there is actual directional information available from the detector. So they would, there will be some amount of ability to say, it seems to be coming from the same part of the sky. But this is not a neutrino telescope by any means.
I'm curious if anybody asked the Fermilab to file an EPA impact study on that beam.
Yes, actually, people do get concerned with shooting beams of particles through their neighborhood, but this was done many, many years ago. Dune is not the first experiment of this time. Fermilab has been making neutrino beams for a long while, and we have pretty good relationship with our neighbors.
Sounds like you're assuming that you can detect with different batch from the source at the destination. You encode it some way, and you're assuming that the wave never catch up with each other.
For the neutrino beams, oh yes. So the neutrinos, they travel at essentially the speed of light from this beam. and the beam structure isn't exactly defined, but it's actually not a continuous hose, it's a pulse. So it's a pulse that's going to be a few microseconds, maybe 5 or 6 microseconds long, and then a gap of about a second to the next pulse, right? And the accelerator that is producing the beam has very accurate timing clocks, to measure to less than a nanosecond when the pulses are happening, and the Dune detectors are connected with that same clock, so they know exactly when the beam should be coming through. Nonetheless, they have a readout window that's nearly 1,000 times, I think, the size of the actual beam delivery. So they'll start streaming data out of the detector, then a pulse will come through, and they'll stop streaming data out of the detector. That's the 6 gigabytes. They'll look at it and say, nope, nothing that time either, and keep on doing that. And maybe 6 or so times a day, eureka, they will have actually seen a neutrino interaction.
So what do you mean if you never get overlap being on the flat? Only have one wave at any.
Well, there's trillions of neutrinos in each of those pulses, but with a detection rate of only one out of in maybe 4 hours, when a pulse is coming in every second, I think that the probability that there will be 2 interactions in any one crossing is it's really, really tiny. I don't know if the detector is probably going to run for 30 years. If they see one of them, I think they'll be excited.
Thank you, Mark. One more question, if you allow. What happened to all this data that collected from 70s and that was on the tapes? Do still people have access to it, to study?
People do have access to it. So unfortunately, without, because they don't traditionally use a well-standardized format, not to name any particular one in this crowd. To analyze the data, you need the software from the experiment. So both CDF and D0 use their own technologies. And so people were able to study the data long after the experiments were done. Computing for CDF and D0 isn't quite finished at Fermilab yet, so people still can analyze that data. But boy, having a better standardized format in our field would sure be nice. Maybe I'll hear something about that as well.
Thank you very much. Thank you. 7 minutes until next session, so feel free to have some.
Next session speakers can come.
Oh, yeah. It's right. So, wait.
We skip time for questions, apparently.